Hello everyone, my name is Elton and I'll be giving a short introduction to compilers. The purpose of this talk is to cover a broad range of topics and not to go into depth into some of the minor details. So the discussion will be rather high level. Uh, we will obviously explore some of these details sometime in the future, but for now, if you don't understand a topic completely, don't worry, you'll be fine. A lot of this material is covered in CS 4240, which is the compiler's course at Georgia Tech, and this is just a speedrun of that. So before we get into talking how a compiler is structured, we need to understand what a compiler is. So the most important thing that I like to keep in mind is that compiler is just a computer program. It's nothing special. It's not some sort of magic that the computer does automatically for you. It's just another computer program. The purpose of this program is to take in text written in one language and transform it to text written in another language. And that other language is typically called the target language. So some forms of the target language include binary. So if you want to create an executable that can be run on a computer, your compiler will output a binary. In other cases, your compiler might output code itself, and that code will serve as input to another compiler. An example of such a thing is TypeScript to JavaScript conversion. So typically, the general purpose of having compilers, or the main reason for having compilers, is you want to transform code that is written in a higher level language to something that's lower level, so that we humans can work on figuring out some of the more abstract details of a particular problem that we're trying to solve, and have the computer sort of figure out how to actually execute some of our abstractions and specifications. A really good website if you want to explore with how compilers take high-level code and convert it to assembly is godbolt.org. It has this nice web UI. You can type in code on one side and see the output on the other. Uh, it happens inside of your web browser, so you don't need to download any special dependencies. Highly recommend to check out this website. So, moving on. Why do I think this field is exciting? So, as I mentioned before, programming languages offer different features, and you can write code different abstraction levels. You could write high level code in a language, so you can just describe your business logic and have the computer figure out how to exactly run it on your machine. Or you could go low level and tell the computer exactly how you want to process certain kinds of data. For example, if you're writing a video encoder, you want to tell the computer how exactly to process the input stream and how to encode and decode the input stream. Um, Another interesting part of compilers is that there are a lot of trade-offs at every level of the stack. So you as a compiler writer will have to make a lot of important decisions. Is your language going to have manual memory management, or is it going to be garbage collected? Do you want your language to be fully compiled or interpreted? Uh, do you want your language to support just object-oriented programming? Do you want it to be functional or even multi-paradigm? Uh, Another challenging question that compiler writers have to face is, how do you make programs run faster? How can you make the best possible use of the target machine? Because ultimately, the whole point is when you write code, you want to have it run on some machine, and it's really nice if you can make that code run faster and have it make the best possible use of whatever environment it's being run on. How can we abstract those details away from programmers and have the compiler sort of automate that process? Um, and then this is sort of an extension. Can we apply these techniques to solving problems in other domains? For example, can we apply uh, sort of compiler optimizations to solve maybe a machine learning task? So that's why I find this field quite exciting. Uh, so moving on, here is the general structure of a compiler. So typically, and now note, not all compilers adhere to this structure strictly. Different compilers have different structures, but overall they sort of fit in this model. So you've got a front end. The front end mainly deals with parsing the text or with parsing the input, which is whatever the programmer writes and codes up, and trying to convert that into a form that the compiler can use to optimize and manipulate and refactor. So that's what the front end does. Consists of two parts, a lexer and a parser, which I'll go over in a little bit. Then you've got the middle end of the compiler, and this is mainly where it does the refactoring of the code. So this can be in the form of optimizations or just moving code blocks around. Um, that's what happens at the middle end. Finally, in the back end part of the compiler, you are taking that intermediate representation of the code that the middle end is using and trying to target it to some particular output language. So it can be binary, another programming language, and there's some interesting parts of the back end, like how do you allocate registers, how do you sort of schedule instructions you're trying to run it on the machine, and how does code generation actually work. Uh, the last point I feel is important. Every stage communicates through an intermediate representation. So you can think of this as a um, representation of the source code is basically a data structure inside of a compiler that represents your source code, maintains and retains all the semantics of the program, but it's just a lot easier to program with and manipulate. So that's the general structure. Here is a diagram. So you've got the lexer and the parser right here. They output some IR. Then you've got multiple optimization passes. So, for example, you can imagine one optimization pass can delete away code that never gets executed. And then you can imagine another optimization pass sort of transforms your for loop into something that's more efficient and so on and so forth. So you can have multiple optimization passes. Each pass produces an IR. So uh, see how the compiler is using this intermediate representation to communicate between different modules. And then finally, you reach the backend, and there are some interesting parts to it. Now, obviously, there can be more parts to the backend. I just listed uh, two important ones, so instruction scheduling and register allocation, but you can obviously have more. And then obviously code gen and optimization. So this is if you want to optimize some low-level code in the target language, if you want to apply some sort of minor optimizations. So yeah, this is the general structure of the compiler. So let's move on to talk about the first part. So we're in the front end of the compiler right now, and we're going to be talking about the lexer. So the whole point of the lexer is take in an input stream. This input stream can be in the form of text or can be something that comes over the network. It's just a stream of input, and then it outputs that stream or it converts that stream into a list of tokens. So what exactly is a token? Token is smallest unit of a particular programming language. So for example, if I write some very basic C code right here, you can imagine a token being the smallest unit that the programming language sort of defines. So the int type over here is type, and that's one unit of the program. The semicolon right here, it is a token of the program. It may not evaluate or anything, but the programming language requires that you terminate all statements with a semicolon, and that's why you think of it as a token. Similarly, main, left parentheses, right parentheses, left brace, right brace. So they're all examples of tokens. Uh, so typically, lexers are simple to handwrite. It's basically you sort of pattern match on what character you're looking at and invoke the corresponding function to lex the rest of the input. But uh, a lot of it tends to be quite boilerplatey in nature, and so people tend to reach out for Alexa generators. OCaml is an example of Alexa generator for the OCaml programming language. Alexa generator basically takes in a high-level description of your language and it will automatically generate source code that will Lex your program. So here's a simple example. You've got some C code right here on the left. It's basically a for loop. It iterates about 10 times and it prints I with the value of I. And here on the right, you have the output of Alexa. So you can see we've sort of classified each token based on whether it's a keyword or if it's just another character, if it's a data type, so on and so forth. So here, for example, 4 is classified as a keyword, the 0 is classified as an integer, semicolon and left paren are their own token types, and so on and so forth. You sort of imagine this being represented in a programming language using the enum construct, or yeah, let's just stick to enums for now. Yeah, so that's an example of Alexa. So once you've lexed the input, the next thing that you want to do is parse and sort of try and understand if the token stream or the list of tokens it satisfies the syntax constraints of the language. And that's exactly what the parser is designed to do. So the parser will take in your list of tokens and it will output the intermediate representation. And along the way, it will check and make sure that your list of tokens uh, it satisfies the syntax rules of the language. So in case you, for example, forget to put a semicolon at the end of a statement, the parser can output an error saying that semicolon is missing. Um, there are different kinds of parsers. So the most popular one is the recursive descent parser. It's most popular because it's pretty simple to write by hand. The other two variants are LR and LL parsers. These are typically auto-generated using parser generators. Similar to a Alexa generator, you have a parser generator. And here are some examples. So Bison and Yak, Menhir, some parser generators. You could also try using parser combinator frameworks. So Parsec and Nom, um, examples of parser combinator frameworks. Uh, they just help you. They just give you a bunch of helper functions that you can use to write your parser. Um, want to elaborate a little bit on recursive descent parsers. So the reason why it's called a recursive descent parser is because at every point the parsing, you will look ahead uh, for, let's say, n symbols, and based on your look ahead, you will invoke a corresponding parse method. And this parse method itself can invoke another parse method. So basically, you can imagine this lookahead process being run somewhere in here, and then it invokes its own other parse method. This parse method returns. Then once that's done, you can imagine this one returning, and so on and so forth. So that's why it's recursive in nature, because um, you can potentially call the same parse method while executing the parent parse method. Recursive descent parsers are easy to write because you can imagine it being some sort of a tree data structure. You're just trying to figure out what level each of the nodes exist. So here is an example of a parser. The output format here is a parse tree. So you can imagine writing a recursive descent parser to sort of produce this parse tree. One interesting point to note here is this parse tree, it sort of obeys the precedence requirements of the operators involved. So, for example, you want to run the multiplication first and only then run the plus and minus. This is because of PEMDAS. The way you would encode that information is by using a precedence table, um, and you would implement a variant of a recursive descent parser known as the Pratt parser. So the Pratt parser basically helps you, or it allows you to encode this precedence information and ensure that the parse tree is structured in the right way. Uh, Feel free to look this up. It's a pretty accessible topic. Yeah, so this is an example of how input gets parsed. So here are some additional notes on lexers and parsers. So if you recall earlier when I spoke about lexer generators and parser generators, you had to provide a high-level description of your language. That is typically provided through a CFG or a context-free grammar. Here's an example of a context-free grammar on the next slide, but just know that this is one way of describing the front end of your language. A common pitfall when writing a context-free grammar is ambiguities. You want to avoid that. So an ambiguity is basically when the parser has to make a choice between multiple possible options for parsing a given token. And you want to avoid that because that will result in non-deterministic output, which isn't good. Um, if your grammar is small enough, it's simple, you can combine the lexer and parser steps into one. So some examples of that include like if you're parsing IRC packets from a network stream. IRC is a relatively simple text format. You can just combine the lexer and parser into one. Key value pairs and CSV files are other simple examples. Um, Here is a context-free grammar. So uh, see here we're defining the program node. We're saying a program can either be a statement or an expression. So the pipe sign here stands for alternation. Essentially, I guess a synonym for that is just or. So it can either be a statement or an expression. Um, Now note here how we define expression. So here we're saying an expression itself can be expression, operator expression, or a variable, or 0 to 9. An operator can be either a plus or minus. A statement is an expression followed by a semicolon. So this basically defines your grammar. An example of a statement that satisfies this grammar is 1 plus 2. So here 1 can be thought of, or 1 satisfies this particular part of the grammar, 2 satisfies this one, plus is an operator, and then this whole part 1 plus 2 satisfies the expression, and the expression is part of the program, so you have a full-blown program. Here there's a short note about left recursive grammars. So if you were to write a recursive descent parser for this particular grammar, there's a chance that your parser would loop forever and would not break out of it because in order to parse an expression, first you have to parse an expression, which is basically a sub-expression. And if this part never ends or it just keeps looping forever, then your parser will also loop forever. The way you solve this problem is by converting this left recursive grammar to a right recursive grammar. I encourage you guys to look it up online if you're not familiar with this and try and see how it's done. There is an algorithm for automatically doing the conversion, and you should be able to easily find it. So once you're done with the front end, the output of that is an IR, which is an intermediate representation. So a succinct definition for that is it's just an internal data structure that's used to represent source code. And one of the main reasons for having an IR, as I mentioned earlier, is that you want to easily manipulate source code. You want to be able to make modifications to it, remove stuff from it, reorder it, refactor it. Different styles of IRs exist, and they allow for different kinds of optimizations. So you can have an IR that is quite low level, allows you to make sort of minute changes to the source code. You can have an IR that is at a high level and allows you to make more global optimizations, observing sort of a global structure of the code. There are different kinds of IR, abstract syntax tree, linear formats, even programming languages can serve as IRs themselves. Yep. So abstract syntax tree is sort of similar to a parse tree, but with some of the tokens just stripped away. Um, you can imagine some of the tokens that are not involved in evaluating an expression. For example, a brace or a semicolon. You just get rid of that, just retain the high level um, components of a particular programming construct. So here in this figure, for example, you're parsing a while loop. A while loop always has a condition and a body of statements. The condition itself has a less than sign, variable, and a constant. In the statements, well, it's a list of statements. You've got an assignment statement. There's a plus operator somewhere in here and a times operator. But you could use a recursive descent parser to build such an ESD, and that should be pretty intuitive to understand because recursive descent parsers allow you to build this tree-like data structure. So pretty straightforward. Now, once you're done with the tree-like data structure, another popular format is to have it be linear. In linear, you can think of as sort of approximately equal to a high-level assembly. High-level assembly. So it's not exactly like x86 or ARM, but it's slightly higher level and more easier to understand. Although there might be some IRs that are quite complicated. Um, the whole point of this is just to have a common format so that different parts of the compiler can talk to each other. So one popular format is stack machine code. So you can imagine having instructions like push something onto the stack or pop something off the stack. So if you're familiar with reversible notation, sort of think of it as adhering to those semantics. Another popular one is the three register format. So this is usual assembly instructions. So you have an opcode, then maybe a couple of registers, um, and different instructions have different sort of encodings. So here are some examples, like this particular instruction adds two registers and stores the result in uh, the destination register. This one here performs a branch. Um, there is this variant of the format. It's called SSA. And SSA stands for single static assignment. I might have gotten it opposite. I think it's static single assignment. I'm not 100% sure, but it's got static and single in the name. So that part I'm sure of. But yeah, so that's this is a variant of the linear format. An extremely popular form of linear IR is the LLVM IR. So the LLVM IR, here's an example figure that highlights that. So you can see over here, there are some instructions that allocate integers on the stack. And here you're storing certain values at those locations, loading them back, and then you're performing an add operation and returning the result back. This sort of looks cryptic, but if you go over the manual of LLVMIR, it will be a lot more easier to understand. But here's an example. The whole purpose of this was to just expose you to linear IR. And then you can also have languages as IRs. So believe it or not, C was used as an IR back in the day. By back in the day, I mean in the 1980s. Uh, some other forms of IR include like JVM and Beam bytecode. So JVM is used by Java and Clojure. Beam is used by Elixir or Lang. family of languages. The newer one is Gleam. I think it compiles to Erlang, uh, and Erlang itself uses Beam. I'm not sure on that, but you can look it up. Some other languages that uses IR include JavaScript. So JavaScript is the input to like bundlers, Corolla Parcel, Webpack. They optimize, minimize JavaScript, and output more JavaScript out. And then WebAssembly, I haven't seen any commercial example of WebAssembly being used as an IR, but you could sort of imagine it being a thing in the future. WebAssembly is, at least the text format, consists of a bunch of S expressions. If you're familiar with Lisp, you probably know what an S expression is, but I'm just going to leave it at that. Have your curiosity sort of drive you towards searching what it means. Yeah, but you could also have languages as IRs. So once you have an IR, you want to do some optimizations on it before you want to sort of come up with your optimization. You want to represent it in a format that can be easily studied. In one format that computer scientists like a lot is the graph format. So you would take your IR and convert it into some sort of graph, and then develop an algorithm that modifies that graph while still upholding some invariant. So one very popular format is the control flow graph, which is used to model control flow, as the name suggests. So wherever you have like a change in control, for example, if you have an if statement or a for loop, um, here in this case it's a branch statement, uh, you basically create a new node for each output that branch statement. So here you have a true part and a false part, um, and the same sort of logic applies to other control statements like the infamous goto. Um, Another popular form of graph that's used in compilers is the data dependence graph and the interference graph. These are used typically during code generation or the backend part, but you could also use the data dependence graph to do some or middle and the style optimizations. Speaking of optimizations, here we are finally at this slide. So one of the main purposes of having a compiler is that you want to abstract and automate away some of the uh, minor details of making your code run faster on a computer. You want a compiler to identify certain patterns and sort of transform them into faster code. And that's exactly what the optimization phase does. So it takes in an IR, modifies it in a certain way, and it outputs another IR. So here's the line that basically says that. Um, an important point to note when writing an optimization pass is that it mustn't change the semantics of the program. So if initially the program added one and one together, after an optimization, it should have just print hello. So you have to make sure that it upholds the semantics. So I don't want to go into too much detail into how to actually come up with an optimization pass, but I just wanted to give some high-level examples. So here is one example of an optimization pass called dead code elimination. So basically, as the name suggests, you get rid of dead code. Dead code is code that will not execute during a run of the program or during all runs of the program. For example, on the left-hand side here, you've got some code here, and then you hit a return. So anything after a return, it won't execute. So it's dead code. After you do that code elimination, you can just get rid of this part, and you get this code block out. Uh, Another example of an optimization is constant value propagation. So if you study this code snippet a little more, you'll notice that x and y are constants. And if you add x and y together, as this expression suggests, you get 10. So 10 equals 10. And that means that you're always going to print the statement, which means that you don't really need to execute the if statement at runtime, so you can just get rid of it. So constant value propagation propagates these constants towards the end expression, evaluates the end expression, and if possible, eliminates it. Um, and after elimination, you end up with this snippet. And that's all I had for optimizations. I'm going to move on to final part, which is the backend. So code generation basically involves taking your IR and transforming it to the target language. There are different possible target languages. So target assembly, for example, and then you have the linker and the assembler convert that into binary. Some low-level languages like C, C++, Rust do that. You can target bytecode, so Java, Elixir, Erlang, Clojure, they output bytecode, which then gets run by a virtual machine. Or you can even target another programming language, so TypeScript, HTML, JSX. There are some examples. Just target the JavaScript programming language. Some of the challenges involved in code generation, mentioned this right at the beginning of the talk, is you want to make the best possible use of underlying architecture. You want to run as many instructions as possible. And if, say, you're running it on a system that doesn't have as many resources, you want to be able to reduce the size of the output. Uh, Typically, if you don't want to write your own code generator, you can just use LLVM. A lot of languages end up targeting LLVM IR and then use LLVM to finish up the whole code generation process. Languages like Rust, Julia, Zig, and even C and C++ with Clang, or I should write that more neatly, Clang, they use LLVM to do a lot of the code generation. So two interesting parts of code generation are register allocation and instruction scheduling. So register allocation basically amounts to if in your IR you use, say, m different registers, but your computer only supports n, and let's say m is greater than n, you want to find a way to map these m registers to n registers. So essentially, you think of having m registers here, so 1, 2, 3, 4, then you've got n registers here, um, and you want to be able to map these different registers together. Um, so it essentially amounts to finding a graph coloring. There are certain algorithms that let you do that. I won't go over them, but just wanted to expose you to this concept. Another interesting part of code generation is instruction scheduling. So um, if you take a high-level computer architecture course, you'll learn about things like pipelining and out-of-order processors. The gist of it is that the computer might reorder instructions in certain ways to gain speed ups, and sometimes there's a cost to executing a certain instruction. For example, if you execute a multiply instruction, um, there's a cost associated with it that's higher than, say, executing an add instruction. Maybe because the multiply circuitry is just larger and it takes more time. So you want to be able to organize your instructions in a way that minimizes the total time that it takes to run your program. And you can do that in a smart way. Um, Now this particular problem is NP hard, so we haven't found the most optimal solution yet. The most popular solution is something called greedy list scheduling. So it attempts to make greedy decisions at each point and tries to arrive at something that's close to optimal. Um, I made this point about NP hard is because a lot of the problems that you might end up trying to solve when writing a compiler, they might either be undecidable or will be one of these NP-complete problems to which we don't know if a solution exists yet, hopefully in the future. But yeah, this is instruction scheduling. And that brings us to the end of the talk. So, in this last slide, I just wanted to go over some topics that I find interesting, um, and hopefully we'll be able to talk about them in future talks. So, asynchronous runtimes, if you ever use the async await, so it basically deals with how it's actually implemented, how different languages approach the problem, and how they sort of incorporate it into their runtimes. Type systems is an interesting topic. A lot of functional programming languages use type systems to give you some static guarantees. Um, some subtopics include type inference. For example, OCaml uses the Hindley-Milner type system, or ML, I should say, and formal verification involves using code to prove properties about code. Uh, Another interesting topic that we can go down and dissect. JIT compilers are gaining popularity. For example, the V8 engine has a JIT compiler that can run JavaScript code pretty efficiently. Um, JIT just stands for just in time. So it attempts to compiler instructions on the fly. If it notices a pattern, it can cache the compilation, just use the cached version again. Uh, yeah, the V8 engine is used in Node.js and the Chromium browser engine, so might be interesting to study how it works. Uh, Domain-specific languages are also getting a lot of popularity these days. Basically, just languages to sort of that match a specific domain more closely. Um, well, domain-specific languages have been around for quite a while, but I just feel like they're an interesting topic to cover. And then finally, we have the dual here, compilers for ML and ML for compilers. So if you look at frameworks like PyTorch, JAX, TensorFlow, Halide, they essentially have a compiler somewhere in their code base that takes your description of your ML model, converts it to some sort of a graph format, and then does optimizations and potentially runs that on hardware. Um, an interesting feature of some of these frameworks is automatic differentiation. So you can think of describing function f in code and then having the computer automatically figure out what its derivative is. This can be super handy. For example, if you have a neural network, um, yeah, this is a speed run draw of neural network. Just imagine there are a bunch of errors here. So you've done your forward pass, and now forward pass, and now you want to do your back propagation. So back propagation essentially involves computing a lot of these derivatives and propagating them backwards. So AD or automatic differentiation engines abstract that away for you most of the time. Be super interesting to see how some of these engines are actually implemented in production code bases. And then ML for compilers involves using machine learning to come up with optimal code sequences. An example project that does this is Compiler Gym. It uses reinforcement learning to figure out better optimizations for code sequences. Um, yeah, that's all I had for today. Thank you guys for listening. Uh, if you have any questions, feel free to post it in the Discord server, and sure there'll be many people who are happy to answer it. Um, a lot of these topics are covered in CS 40 at Tech, so if any of this piqued your interest, feel free to take the class. I think it's an interesting class. It's pretty project driven. So yeah, that's all I had. I'll see you guys next time.